The story of Janos Bolyai. Janos Bolyai was born in the Transylvanian town of Klausenburg. He is a son of Susanna Benko and the well-known mathematician Farkas Bolyai. By the age of 13, he had mastered calculus and other forms of analytical mechanics and receiving instruction from his father. He studied at the Imperial and Royal Military Academy in Vienna.
Before Janus Bolyai attempted to prove the Euclidean parallel postulate, his father gave him a warning through letter.
You must not attempt this approach to parallels. I know this way to its very end. I have traversed this bottomless night, which extinguished all light and joy of my life. I entreat you, leave the science of parallels alone. I thought I would sacrifice myself for the sake of the truth. I was ready to become a martyr who would remove the flow from geometry and return to its purified mankind. I accomplished monstrous, enormous labors. My creations are better than those of others, and yet I have not achieved complete satisfaction. I turned back when I saw that no man can reach the bottom of the night. I turned back unconsoled, pitying myself and all mankind. I admit that I expect little from the deviation of your lines. It seems to me that I have been in these regions, that I have traveled past all reefs of this infernal Dead Sea, and have always come back with broken mast and torn sail. The ruin of my disposition and my fall date back to this time. I thoughtlessly risked my life and happiness.
This is the reply of Janos Bolyai from the letter of his father.
It is now my definitely plan to publish a work on parallels. As soon as I can complete and arrange the material and an opportunity presents itself. At the moment, I still do not clearly see my way through. But the path which I have followed gives positive evidence that the goal will be reached. If it is at all possible, I have not quite reached it, but I have discovered such wonderful things that I was amazed, and it was be an everlasting piece of bad fortune if they were lost. When you, my dear father, see them, you will understand. At present, I can say nothing except this, that out of nothing I have created a strange new universe. All that I have sent you previously is like a house of cards in comparison with a tower. I am no less convinced that these discoveries will bring me honor than I will be if they were complete.
It seems to me advisable if you have actually succeeded in obtaining a solution of the problem, that for a twofold reason. Its publication be hastened. First, because ideas easily pass from one man to another who in that case can publish them. Secondly, because it seems to be true that many things have, as it were, an epoch in which they are discovered in several places simultaneously, just as the violets appear on all sides in springtime.
The letter of Ghost to his friend Farkas Bolyai.
If I begin with a statement that I dare not praise such a work, you will of course be startled for a moment. But I dare do otherwise. To praise it would amount to praising myself for the entire content of the work. The path which your son has taken, the results to which he is led, coincide almost exactly with my own meditations, which have occupied my mind for from 30 to 35 years. On this account, I found myself surprised to the extreme. My intention was, in regard to my own work, of which very little up to the present has been published, not to allow it to become known during my lifetime. Most people have not the insight to understand our conclusions, and I have encountered only a few who receive with my particular interest what I communicated to them. In order to understand these things, one must first have a keen perception of what is needed, and upon this point the majority are quite confused. On the other hand, it was my plan to put all down on paper eventually, so that at least it would not finally perish with me. So I am greatly surprised to be spared this effort, and am overjoyed that it happens to be the son of my old friend who outstrips me in such a remarkable way.
And now, the mathematician Janus Bolyai became obsessed with a parallel postulate.
In particular, Bolyai became obsessed with Euclid's fifth postulate, or often referred to as the parallel postulate, a fundamental principle of geometry for over 2 millennia, which essentially states that only one line can be drawn through a given point, so that the line is parallel the interior angles of a triangle sum to 180 degrees or two right angles. In fact, he became obsessed to such an extent that his father warned him that it may take up all his time and deprive him of his health, peace of mind, and happiness in life. A tragic irony given the unfolding of subsequent events. Bolyai, however, persisted in his quest and eventually came to the radical conclusion that it was in fact possible to have consistent geometries that were independent of the parallel postulate. In the early 1820s, Bolyai explored what he called imaginary geometry, now known as hyperbolic geometry, the geometry of curved spaces on a saddle-shaped plane where the angles of the triangle did not add up to 180 degrees and apparently parallel lines were not actually parallel. In curved space, the shortest distance between 2 points A and B is actually a curve, or geodesic, and not a straight line. Thus, the angles of a triangle in hyperbolic space sum to less than 180 degrees, and two parallel lines in hyperbolic space actually diverge from each other. In a letter to his father, Bolyai marveled, "Out of nothing, I have created a strange new universe." Although it is easy to visualize a flat surface and a surface with a positive curvature, example, a sphere such as the Earth, it is impossible to visualize a hyperbolic surface with negative curvature, other than just over a small localized area where it would like a saddle or a Pringle. So, the very concept of hyperbolic surface appeared to go against all sense of reality. It certainly represented a radical departure from Euclidean geometry, and the first step along the road which would lead to Einstein's theory of relativity among other applications. Although it still fell well short of the multidimensional geometry which was to be later realized by Riemann. Between 1820 and 1823, Bolyai prepared but did not immediately publish a treatise on a complete system of non-Euclidean geometry. His work was, however, only published in 1832, and then only a short exposition in the appendix of a textbook by his father. On reading this, Gauss clearly recognized the genius of the younger Bolyai's ideas, but he refused to encourage the young man and even tried to claim his ideas as his own. Further, this heartened by the news that the Russian mathematician Lobachevsky had published something quite similar 2 years before his own paper, Bolyai became a recluse and gradually went insane. He died in obscurity in 1860, although he has only ever published the 24 pages of the appendix. Bolyai left more than 20,000 pages of mathematical manuscripts when he died, including the development of a rigorous geometry concept of complex numbers as ordered pairs of real numbers. Completely independent from Bolyai, In the distant provincial Russian city of Kazan, Nikolai Ivanovich Lobachevsky had also been working along very similar line as Vallier to develop a geometry in which Euclid's fifth postulate did not apply. His work on hyperbolic geometry was first reported in 1826 and published in 1830, although it did not have general circulation until some time later. This early non-Euclidean geometry is now often referred to as Lobachevskian geometry or Bolyai-Lobachevskian geometry, thus sharing the credit. Gauss claims to have originated but not published. The ideas are difficult to judge in retrospect. Other much earlier claims are credited to the 11th century Persian mathematician Omar Khayyam and the early 18th century Italian priest Giovanni Saccheri, but their work was much more speculative and inconclusive in nature. Lobachevsky also died in poverty and obscurity, nearly blind and unable to walk. Among his other mathematical achievements, largely unknown during his lifetime, was the development of a method for approximating the roots of algebraic equations, a method known as the Dadelin graph method, named after two other mathematicians who discovered it independently, and the definition of a function as a correspondence between two sets of real numbers, usually credited to Dirichlet, who gave the same definition independently soon after Lobachevsky.